Now in this question, you were asked to make up a standard buffer, and in part A, you were asked to identify which one is the acid, which one is the base, and you were basically given these two components here, and you had to decide which one is the acid. So very clearly for part A, you would have to say that this one here is the acid, just simply because it has H2 phosphate, and this one here, this is the base, because it has HPO4 2-, and this one has one proton more than the corresponding conjugate base. So this one therefore would be the acid. So and an acid can give off proteins, whereas the base can accept the protein. So for part B, determine whether you need more acid or base to achieve the desired pH. Well, we said if the pH is lower than the pKa, we need, the whole thing is more acidic, and therefore we need more acid. If it was the other way around, if pH is higher than the pKa, then it would be more basic and we would need more base. Now, very important, please don't confuse it with pH and the neutral point. So some people said that because the pH is lower than pH 7. Now, unfortunately, this is not how it works. It does not mean that if the pH is lower than 7, it is the pKa that is actually the important bit here. Now for the next question, for question C, we are asked about the ratio that we need, and we know we need more acid, so we can easily use the Henderson-Hasselbalch equation, say pH equals pKa minus logarithm of acid to base. Now we have to rearrange this equation a little bit. We get log acid over base equals pKa minus pH, and that is 7.2 minus 6.5, and of course that is 0.7. Now, in order to get rid of the log, we take both sides 10 to the power of, so we have A over B equals 10 to the power of 0.7, and that equals 5 to 1. So we need 5 parts of acid and 5 parts of base. Now for the next part, how many moles of acid and base respectively are required to achieve the desired pH and the desired capacity. Now be careful, it says here how many moles. So we're looking for an amount, and we know that it is 200 millimolar phosphate buffer and 500 milliliters. So what we have here is 500 milliliters and a total amount of 200 millimolar phosphate. So now we need to calculate how many millimoles phosphate we need in total. So millimoles phosphate, and we can do that with dimensional analysis. So we have 200 millimole per liter, that's from here, times 500 milliliter, I just write it as 0.5 liter. It cancels out, and I get a total of 100 millimole. of phosphate. So I know that A plus B, acid plus base, equals 100 millimole. And I know that A over B, or the ratio, equals 5. So I have two equations and I can solve this. So for A, I can say A equals 5 times B. Put that into this equation here. So I have 5 times B plus B equals 100 millimole, and therefore B equals 100 over 6 millimole, and that would be 16.67 millimole. And for A, obviously I get 100 millimole, should be a milli, 100 millimole minus 16.67, and that is 83.3 millimole. Now some people have calculated that for the concentration, which per se is not wrong. So they got actually twice the concentration. So they would have got around 33.3 millimolar, and here 100 and something, 166 millimolar. But at the end of the day, you still need to convert this concentration then into mole, and you have to then multiply it by this volume. So you can't get away with that. So then for the next part, we need to find out how much of the acid and the base we have to weigh in, and we've got the molecular weights here. So that's not particularly difficult. What we can say is that we need, of the acid, we need 83.3 millimole, and we have a molecular weight of 136.09 gram per mole. And we can do that with dimensional analysis. So we can say 136.09 gram per mole times 83.3 mole per millimole, I should say, millimole. And when we do this calculation, we get 11.34 gram. And the same we can do for the base. So for the base, we said we need 16.6 millimole, and we have a molecular mass of 142.1 gram per mole. So we get 142.1 gram per mole times 16.6 times 10 to the minus 3 mole, and that gives us 2.4 gram for the base. Okay, now for the other components, we want to have 100 millimolar sodium chloride. How many grams? So we have 58.4 gram per mole. times 100 times 10 to the minus 3 mole per liter times 0.5 liter, and this gives us 2.92 gram for the sodium chloride. Now we have a 0.1% weight per volume BSA. So 0.1 actually means 0.1 gram per 100 milliliter. That's the definition of percent. Since we have 500 milliliter, we just multiply that by 500 milliliter and we get 0.5 gram for the BSA. And for the EDTA, we can use, for example, C1V1 equals C2V2 or doctor divided by pharmacy. So we have 5 millimolar stock. We want 500 milliliter, but we only have 100 millimolar stock, and what this gives us is 25 milliliter of the EDTA solution. Now let's look at the rest of the questions here. So we have 1 milliliter of 1 molar hydrochloric acid. So what is the pH of 1 milliliter of 1 molar hydrochloric acid? Now pH does not depend on the volume. That's something that a lot of people went wrong with. So for the pH, all we need to do is pH is negative log of the concentration of the acid, and that is 1 molar. So the concentration of the acid, I probably shouldn't write this here with a unit. So for log 1 we get 0 and negative 0, but that doesn't matter. So in this case pH equals 0. It does not, we don't need to take this 1 milliliter into account. Now how many moles of hydrochloric acid are in 1 milliliter? So again we are looking for a mole, and we have 1 mole per liter, that's our 1 molar solution, and we have 1 times 10 to the minus 3 liters, so this cancels out, and this gives us 1 millimole of hydrochloric acid that we have here in our 1 milliliter. Now we said previously we had 83.3 millimole of acid and 16.6 millimole of base. And if we add 1 millimole of hydrochloric acid, we would get a new acid is 83.3 plus 1 millimole, which is 84.3, because the acid content increases, whereas the base content 16.6 decreases. The base is converted basically, and by the amount of the acid that we add, so that would be 15.6 millimole. And that is what I expected here. And finally, what we can do now is we can use our Henderson-Hasselbalch equation to calculate the new pH. pH equals pKa minus log, and now we have 84.3 divided by 15.6. Here we had 7.2 for the pKa. And if we do that, the new pH would be 6.47. So in our solution, we originally had a pH of 6.5 in the buffer. Our 1 molar hydrochloric acid had a pH of 0, but if we add this together, then we get 6.47, and that is the principle of a buffer. I hope this makes sense, and thank you for watching.